Okay, it is 2 minutes after and people are coming in, but I think we will get started. So welcome everyone. I'd like to thank you for joining us for today's webinar on understanding and planning geothermal installations in existing municipal facilities. My name is Catherine Wilson. I'm the manager of the Mayor's Megawatt Challenge, a program working with municipalities to reduce energy use and emissions in their own facilities. We're continuing our theme of practical pathways to net zero carbon buildings. Geothermal energy is a critical component in the pathway to net zero carbon buildings. However, there's limited information regarding installation, operation, and maintenance of geothermal systems, especially with respect to municipal buildings. So we're diving into this important topic in 2 webinars. So on May 25th, which was Geothermal Webinar Part 1, we explored geothermal in existing municipal facilities, including factors for successful installations, as well as some common issues encountered with existing systems and how they can be addressed. So procurement was discussed, including what municipalities should be asking for to ensure successful installations. The recording and the Q&A from this webinar will be posted very soon on the MMC Mayor's Megawatt Challenge website and distributed to all attendees of that webinar. So today for Geothermal Webinar Part 2, we will be exploring geothermal, again, in existing facilities in more detail, including hybrid ground source heat pump optimization and thermal imbalance, so solar assisted ground source heat pump design. So as with the Part 1 webinar, the aim is to really provide some practical assistance to municipalities that both have existing systems that may or may not be working and what they'd look for in installing a system in an existing building. So here is the agenda for today's webinar. So we'll start with the welcome and introductions, set the stage, and then dive right into the details on hybrid ground source heat pump optimization and thermal imbalance. And we'll follow with an ice rink example and a Q&A session. So just some instructions. So please reserve the chat for technology related questions or questions unrelated to content, and make sure the message is sending to panelists. If you have any questions related to content, please use the Q&A option. Questions will be answered during the Q&A session, which will be at the end of the webinar, so probably starting about 12:30. And any question we can't get to will be circulated in a question and answer document after the webinar. Okay. So just to give a bit of background again, this will be very familiar to a lot of people on the line, but just wanted to give some context for those who are not familiar. So the pathway to zero carbon buildings follows a systematic process to identify 4 areas of the integrated solution. So first, energy efficiency to improve operations and equipment efficiency, and heat recovery to put as much of the waste heat as possible back into the building. And then integrating renewables, including geothermal, to cover the remaining demand, and leaving purchased carbon credits and other offsets as the last resort. So as I mentioned, we see geothermal energy as a critical component in the pathway to zero carbon buildings. And given the aggressive net zero goals of many municipalities, it's crucial for municipalities to better understand how it works so they can better plan for geothermal installations and resolve any issues with existing installations. So I'd now like to introduce today's speakers, Dr. Seth Dworkin, who is a professor at Ryerson and co-founder and president of WJS Energy, and Dr. Jamie Fine, who's a postdoctoral researcher at the University of Toronto and co-founder and COO of WJS Energy. I'll now turn it over to Seth and Jamie to introduce themselves further and dive right into today's topics.
Thank you very much, Catherine. So I'm just going to switch over to my screen sharing. Hopefully that works. So just give me a thumbs up if my slides have appeared. Okay, great. So thank you very much for the introduction. So my name is Dr. Seth Dworkin. I'm a professor and a Canada Research Chair at Ryerson University. I completed my PhD at Yale University, and I'm also a licensed professional engineer. I've been studying geothermal energy for about 10 years. I've published 50 journal articles on the efficient use of energy, pollution mitigation, and geothermal HVAC systems. And I've written about 20 or so technical and consulting reports on clean energy systems, hybrid ground source heat pumps, which I'll talk about today, a lot of economic projection work and optimization work as well. And with me is my colleague, Dr. Jamie Fine, who's a postdoctoral researcher at University of Toronto. He completed his PhD at Ryerson University, is also a licensed professional engineer. He is the manager of the Center for Climate Science and Engineering at the University of Toronto. He's published 9 journal articles on solar energy heating, geothermal HVAC, low energy building retrofits, and worked on about 6, actually I think after today it'll be number 7, right Jamie? 7 technical consulting reports. We were finishing one this morning on solar assisted heat pumps, economic projections, and HVAC optimization. So a little bit about WJS. So WJS Energy is a private company that we also that we run. It specializes in planning and understanding geothermal installations for a variety of different types of clients in governments, municipal and federal, private sector, education sector, and so on. And we use a suite of innovative techniques to analyze and plan leading edge sustainable building energy systems. We help advise and we help do all the calculations needed to complete the process and understand costs and operation and efficiency and so on. So we're here to talk about ground source heat pumps, often referred to as geo-exchange systems. So here's sort of a schematic. I'm just going to switch now to my laser pointer. Okay. So here we've got a building, some sort of dwelling that's got a heat pump, which is hooked up into a vertical ground loop. And so the ground acts as a long-term thermal battery connected to the building. And the ground can also replenish and reject some of the heat. So it's not sort of a pure thermal battery because it is sort of connected to the soil and to the air and so on. So geo-exchange systems are a really great sustainable technology, but they only account for about 1% or a little less of all HVAC in Canada. And I've always been interested in this question, why? Why so few, especially compared to European economies where sometimes they're upwards of 50%. And the main reasons that I've come across over the years in my studies have been larger capital costs, usually associated with having to drill really deep boreholes, and thermal imbalance, and I'll explain in more detail what that is. But when systems are not properly designed, they can underperform and prove very costly with the concept of thermal imbalance. And thermal imbalance, very, very simply, can arise when the heating demands of a building are vastly unequal to the cooling demands of a building throughout a year. So we're in a seasonal climate, and we need to kind of roughly balance the amount of heat that goes into and out of the ground. So the first topic I'll dive into is hybrid ground source heat pump optimization. Then I'll talk a little bit more about thermal imbalance. So hybrid ground source heat pump optimization. So here's a simple schematic of a hybrid ground source heat pump. You've got a building of some sort. It's hooked up to a ground loop and a ground source heat pump. There may be a cooling tower rejecting heat to the air from the ground loop. There might be some other conventional HVAC system, maybe a boiler, and that's a hybrid system. So you've got multiple systems providing heating and cooling, and this is pretty typical in larger buildings, so in the commercial sector or multi-residential. So if you consider what the heating and cooling demands look like for a year, so many of you have seen curves like this, but along the x-axis are hours from 0 to 8760. So 0 is January 1st, and that's an entire year. There are 8,760 hours in a year. And this is a heating demand graph. So in January, February, March, we need heat. We don't need any heat in the summer, and then it ramps back up again in October, November, December. The cooling graph can look very different. In this particular building, there was, I believe, a server room which needed cooling all year round, but it it peaks in the summer. So this is what you might get from monitoring building needs, or more directly from building energy simulation, where you simulate the needs of a building. And so you can see that peak demands up here only occur for a very short time in winter and a very short time in summer. So if we focus on the cooling demands, some designers don't practice what we call peak shaving, and others use 70, 80, or 90%. And what that basically means is that you draw a line across the demands across a year, and every time the demand is below that line, it can be met by your geothermal system. And then every time it exceeds the capacity of the geothermal system, which is this black dashed line, the demand needs to be met by some auxiliary system. So maybe in this case, an air source heat pump or some other type of chiller system. And so where to draw that line is very key. If you draw that line too high, you'll have too large a ground source heat pump that you'll need to install. And the payback period on that will be very long because it won't be used to its fullest extent. But if you draw that line too low, you'll have too small a ground source heat pump, and that will offset too little of the conventional heating and cooling system costs and also have too long a payback period. What we've found is that about 90% of all buildings, and we've looked at Canada and the United States, different types of buildings and different types of usage. So some residential, some that are used 24/7, others maybe business, used primarily Monday to Friday, 9 to 5. About 90% of buildings have a sweet spot, which is an optimal ground source heat pump capacity that minimizes payback period and maximizes return on investment. In about 10% of buildings, a ground source heat pump is not recommended because it's not going to be utilized to its fullest extent, or we're not going to be able to properly balance heat into and out of the ground. I should say that for those 90%, there may be huge variation in the strategy of designing the ground source heat pump. And I'll talk a little bit more about that in a minute. So how do we figure out how much of a ground source heat pump a building needs? Well, we like to use computed hourly heating and cooling loads from a building energy simulation, often for existing buildings like we might be interested in today, for example, existing municipal facilities. We might look at historical energy consumption as well to make sure that our predicted energy consumption is accurate. And then using 1% increments, we'll look at, say, 100 different ground source heat pump capacities, looking at simulating larger and larger systems. And for each of those 100 iterations, we'll consider all costs of installing and running the conventional systems, as well as the geothermal systems, and make a comparison. So then we'll determine the installation costs, the operational savings, and use that to find a minimum net present value. And so we want a minimum net present value. Many of you might think of different investments and return on investment where you want to maximize your net present value. We're minimizing net present value because it's the net present value of costs of drilling, costs of installation, cost of operation. And we use a net present value, which basically just takes annual recurring costs, such as utility costs, and brings them back to present day costs using an inflation rate, maybe an interest rate as well, so that they can be compared to, say, the higher installation costs of a ground source heat pump. So how does that actually look? So we can look at that graphically. Here on the y-axis, we have costs, and on the x-axis, it goes from 0 to 1. 0 represents no geothermal system. This graph is for one particular building. Say any particular building, we would generate a graph like this. 1 would mean all geothermal. We're meeting peak loads with geothermal. And anything in between, say 0.6, would be a hybrid system where 60% of the peak loads is met by the geothermal, and the remaining 40% would be met by an auxiliary system. The green curve is initial costs, which is primarily installation or drilling costs of the geothermal system. It's 0 down here if you have no geothermal system. And then as you would look at a larger and larger geothermal system, the installation costs, because of the additional drilling requirement, increase. We can add to that curve operational costs. This is primarily utilities. So the cost of the natural gas of a boiler, cost of electricity to run both the ground source heat pump and maybe a chiller or air conditioning system. And in fact, reduced CO2 and maintenance costs can also be considered on an annual basis. And so not surprisingly, if you don't have a geothermal system, the annual costs are the highest. But as you install a larger and larger geothermal system, the annual operating costs come down. And they kind of level off here at around 60 or 70%, because very few times throughout the year do the demands exceed the capacity of 60% of the peak demand, which means you would be meeting most of your energy demand with your geothermal system. The green curve is initial costs, the red curve are annual operating costs, and we can combine those into a net present value of total costs. And then we search for the minimum of that curve. And that curve tells us where the financially optimal point is for the building. So how does that look for an actual building? So we ran this analysis. We run it for many, many types of buildings. Here's an example, which is a school in Southern Ontario. We found that if the ground source heat pump met 53% of the peak demand, that was the financially optimized system. That resulted in ground loops of 4,400 feet, but it met 95% of the total energy demand. So even though it only met 53% of the peak, it was meeting 95 of the total annual energy demand, because those peaks were only accounting for 5% of the energy demand. And what's interesting is if we were to go from 53%, almost doubling the capacity of the geothermal system, up to 100%, we're about doubling the ground loop, the amount of boreholes, we're only meeting 5% more of the energy demand. That's really key. That means going from 53% to 100% can be considered throwing good money after bad. That drilling cost would be much better spent on a different building where those additional boreholes are going to be used for base loads. Here's another example. This was a 75-unit residential mid-rise where, again, the optimized point was at 60%, and we calculated that it met 98% of the total energy demand. So if you go from 60% to 100%, you increase the ground loop length, it's a negligible amount of energy. It's only 2% more energy supply that you're meeting. And it brings down the payback period from 13 and a half years if you went 100% geothermal, down about 4 years to 9.7 years. So that's really key. There's also financial risk mitigation built in there as well. So finances are not the only motivation to put in geothermal. Of course, it's a sustainable energy, and we want to look at the impact of CO2 emissions. So here's a similar graph where I've got CO2 emitted per year on the y-axis versus, again, 0 to 1. No geothermal system at 0, which has the highest CO2 emissions because it assumes that you're burning natural gas for your heating otherwise. And then at 1, you've got the lowest you've got the lowest carbon emissions. And that's really just from the electricity mix, so it gets very low. But at 60%, you're pretty close to your minimum CO2 emissions because it's meeting most of your energy demand. So as this curve begins to flatten out, you don't want to push your system to the right. You want to cap the size of your geothermal system, generally speaking. So a few remarks on this. Rigorous mathematical methods, they take the guesswork out of design and allow designers, operators, owners, et cetera, to rely on hard numbers and financial and CO2 projections. Using these types of mathematical methods result in, on average, payback periods being reduced by about 4.5 years. And really, it's quantitative planning, and quantitative planning is the key. That's the sort of message I really want to hammer home, that ensures that geo-exchange systems are only being installed when appropriate and sized correctly. It also permits the installation of ground source heat pumps that might not otherwise be economically viable. So because it brings down the payback period, it can bring it into a range which is considered viable sometimes. And that adds additional environmental benefit. And yes, the hybrid system assumes natural gas boilers for peaking. You can also you can substitute in any type of peaking system for either heating or cooling. We've done this with propane, we've done this with electric. It changes the inputs to the calculation and can change the result. And so the key is that the calculation gets tailored for every specific building. The next topic I want to talk about is thermal imbalance. So thermal imbalance is a really key consideration in geothermal systems. So this sort of cartoon graph here shows what that means. Along the x-axis, I have time in years. Here's what 1 year is. And along the y-axis, I have ground temperature. And it zigzags, it fluctuates. So the ground temperature will drop in winter as heat is extracted from the ground into the building. And then here's the spring as it turns around. And in the summer, as heat is injected back from the conditioned space into the ground temperature rises. And that annual process continues. Ideally, you want that curve to be low. If it's too hot or too cold, it'll start to reduce your efficiency or lead to system failure of a ground source heat pump. If it's too hot, it won't be able to accept heat in the summer and you won't be able to cool the space. If it's too cold, there will be no more heat to effectively extract in winter and you won't be able to heat the space. In Canada, we usually see heating demand outpacing cooling demand. So we often get the too cold curve. It's not always the case, especially recently I've seen with meeting stricter and stricter sustainable energy standards, that the building envelopes are getting tighter and tighter. And so more and more heat is being trapped in, which of course is generally a good thing, but it's a design consideration because then you can get the too hot curve. System COP. COP is coefficient of performance. It's a way we measure efficiency of these systems. Will diminish usually in around year 3 or 4 in the too cold or too hot case, reducing return on investment. And many geothermal systems have had that happen. So using finite element modeling and building energy simulation, we will model out over time, over 20 years, what the ground temperature will be with a proposed design before it's installed. So here we've done that for a proposed design for a hospital. The ground started at 10 degrees. I've got 3 different points in the ground at different distances away from the boreholes. But the point is that the curve is pretty level. It only drops about half a degree over 20 years. That's quite good. Here was for an apartment building and it was dropping about 5 degrees over 20 years, about 3 or 4 degrees in the first 10 years. And that was quite bad because then the ability of the system to provide heat in winter was compromised and the efficiency was dropping. And on really, really cold days, it means the building might not be able to reach its set point. So the models can predict beforehand if thermal imbalance will become an issue. Another thing we've done is after a year or two, or sometimes after, like in a recent project, after 25 years, we will do an on-site assessment to diagnose the ground to see if its temperature has migrated up or down, because there are ways that that effect can be mitigated. So measurements can be taken on site to make sure that that's not happening, to verify what the models tell us. Where there is significant risk of a problem, we'll usually propose solutions that will ensure longevity. For example, if the ground temperature is going to be too cold, we will implement an auxiliary heating system, and that ties back into the hybridization I talked about earlier. One of the auxiliary heating systems we've looked at recently are solar systems, so solar-assisted ground source heat pumps. So here you'll have solar thermal panels on the roof of a building and a ground loop. And if there's much greater heating demand, then the winter will draw heat out of the ground. And in the summer, instead of putting heat from the building back into the ground, although you might do some of that, we'll put solar heat back into the ground to sort of charge up that battery in advance of the next winter. So our first solar assisted ground source heat pump went into the Evergreen Brickworks heritage site in Toronto in their kilns building. It's the first such system in Canada. The GeoExchange system had 40 boreholes of 600-foot depth, and that was about 480,000 installation, and then 230 solar thermal panels, which are being installed now at about roughly $470,000. And our calculations determine this number and what the costs and payback periods would be. Here's an image of the driller putting in those boreholes. They were in an existing building, so they went down on an angle to get the boreholes under the building to take advantage of a larger volume of ground. This is a photo of the inside of the building. It was hooked into hydronic heating and cooling through a radiant floor. It's to be used as an event site for weddings or corporate events in the future. When we determined the amount of solar panels needed, we looked at optimizing efficiency, optimizing cost, and so on. And so we were able to calculate this table using our simulation approach. So with no panels, we had system failure after year 1, with 50 panels after year 2, and so on, until we hit about 225 panels, where that balanced out the ground temperature curve and made it such that the system would maintain its high efficiency indefinitely. I'm going to turn things over to Dr. Fine now to discuss the ice rink example.
Thank you, Seth. All right. Yeah, continue. Just gotta share my screen here. Okay. Oh, there we go. Can you? Wait, no, this might break it. Can you see my screen?
Yep.
Okay, excellent. So I'm just going to go over a quick example that's pretty relevant to a municipality. And one project I'm working on right now as part of my role at the University of Toronto is investigating the retrofit of ice rink facilities. So municipalities have really started to target these facilities because they're very high energy use intensity. So I've been looking at that, and one component of this project was looking at the installation of a GeoExchange or a geothermal system in the ice rink. Specifically, the example building we looked at was located in King City. It's called the Trison Center. This building is actually rather sophisticated. It uses energy recovery from the ice making system with its HVAC system. So the heat that it takes out of the ice sheet, it actually uses to heat the building, and it can improve the energy efficiency of the building because of that. And then on top of that, which is actually really fortunate and something that, the more time we're spending working on projects, it's just becoming more and more apparent that having this detailed building automation system data, so the BAS data, collected and logged for at least a year, and actually logging a bunch of points in the building, it really helps to determine what type of retrofit you can move forward with in the building. And it really helps to understand how a building's performing. So just to move a bit quickly here, here's just a high level schematic of what the building energy system, at least from our perspective, look like. And I'm just gonna do the same laser pointer. Actually, I'm just gonna use a pen. So as you can see over here, this is the HVAC and ice making system. So as I said before, these two systems are coupled together through energy recovery. So if the building needs heat, it can actually take the heat out of the ice sheet and move it into other areas of the building to save energy. So you're not using a boiler, for example, to heat up something that would use in a hydronic system. But there are still times that this building requires heat to be added. So when this energy recovery can't meet the heating demand, a boiler will be used and supply some heat into it. Alternatively, if there's too much heat accumulation in the system, an auxiliary chiller will be used. And this can be thought of as a hybridized system where you have, energy recovery, then hybridize with these, a boiler and a chiller. And then on top of that, there's the domestic hot water demand, which is supplied by the boiler. But the way that we approached investigating, can we add a GeoExchange system to here is, well, maybe we can reduce dependence on the boiler and on the chiller. So the proposed ground source heat pump would go in trying to offset some of that boiler load and offset some of the chiller load. Because again, these are going to be, it's a more high efficiency type system. But again, this is a building with energy recovery, and we're trying to just offset the auxiliary loads. Okay, so how was the analysis approached for this building? Well, number one, reviewing the system drawings. So coming up with that schematic on the previous page, that wasn't something you could just go and look at the outside of the building and decide, oh, that's how we're going to install a ground source heat pump. What I went through was looking at the detailed mechanical layout in detail, looking at the building automation system data and saying, okay, this is where the ground source heat pump could fit in. And as I said before, we collected and analyzed building automation system data. And shown over here are the thermal cooling and thermal heating loads. So this isn't just electricity. This isn't just natural gas consumption. It's the actual thermal load that would be met by that ground source heat pump, drawn in the way that was shown on the previous slide. So as you can see, notice that this is the same scale. You have 1200 kilowatts and 1200 kilowatts over here. Notice how much higher that cooling demand is. And this kind of leads back to what Seth was talking about with ground thermal imbalance, which I'm going to talk about in a second. So step two, analyze building automation system data to understand what the loads are that are needed for the ground source heat pump. And then go through the process, that optimization process that Seth discussed before. So what happened? Well, here are the same type of financial plots that we saw before. So the green, again, is the initial cost, so mainly the cost of drilling. The red is the operating cost. So as time goes on, as you have a larger and larger ground source heat pump system, you're reducing the operating cost of the system by improving its efficiency. But then when you add them together, you get the net present value. As you can see, in this curve for this specific building, given its specific makeup, it actually wasn't an overly favorable installation. Maybe at a small level, it is within the calculation error. They could say, oh, anything up to about 20% might be reasonable if there are other considerations to make. But based on the inputs, there was no very, very noticeable optimal point from a financial perspective, even though the curve did remain relatively flat in the smaller system size. But okay, so if we could justify spending roughly the same amount of money, there's no large financial penalty to installing it, maybe there's some CO2 savings that can go along with this installation. And that's shown on this graph. So shown again on the horizontal is increasing ground source heat pump size. And as you can see, the CO2 emission, actually, this is just pure emission. It's not emission reduction, but shown on the vertical is going to be the CO2 emissions of the system as a whole. As you can see, once you get to about this point over here, you level off. So even with a rather small ground source heat pump system, you can offset a bunch of the emissions from the system. And the reason for that is, if you remember from the previous slide, the boiler energy, the heating energy consumption, that's met by a boiler. And once you have a rather small system size, which only meets a portion of that large cooling demand that I showed before, you can meet a lot, if not all, of the heating demand. And the majority of the CO2 emissions from this system come from that heating demand. So once you get to a ground source heat pump system size, again, based on the cooling demand, which is the peak capacity of the system of about 5 to 10%, you're meeting all of the, you're reaching the reduction in CO2 that you're going to meet even if you had a 100% ground source heat pump system. So it stabilizes rather quickly. So maybe it's justifiable to install a small system here. But remember, it's not just about the finances. It's not just about the CO2. You need to install a system that's going to work and work for a long time. So what does this ground thermal imbalance, what does that look like for this system? Well, unfortunately, it doesn't look very good. And that's because this is a heavily cooling dominated load that needs to be met. There's a lot more energy that needs to be rejected from the system. So what this curve is showing is, again, with increasing ground source heat pump size, the temperature change of the ground over 10 years. And as you increase the size of the heat pump, you have this peak temperature change of the ground. And at about 7 degrees, it's going to increase in temperature. And to us, that would mean that in a short period of time, this system could fail. And overall, it really shows that it's not just about looking at finances. It's not just about looking at CO2 offset. There's a lot that you do need to consider. It's on a building specific basis to see what this thermal imbalance might look like and actually justify whether or not a system can be installed in the building. And unfortunately for this building, at least based on how we've looked at installing it, so for example, domestic hot water still being met by a boiler, we're seeing a ground thermal imbalance issue with this building, and we wouldn't recommend installing the system. And again, it's important to check. You can't just assume it's going to work because it's financially potentially justified, but you need to go and check if the longevity of the system is going to be okay. And as I said a second ago, based on the current system and what we're expecting the loads to look like right now, we don't recommend integrating a ground source heat pump with this building. And yes, this is not the most positive example, but at the same time, it shows the importance of checking, because 90% of buildings can work with ground source heat pumps, but this specific building did not. And we felt this was an important example to share because it shows how important it is to double check, or else you're going to run yourself potentially into a problem where you have a system that doesn't work and you may not even know why. Okay, so now we're at the recap, and I think Seth is just going to go over these last few points.
Sure, but I'll let you continue with the slide. Okay, can you give me a few more points here to advance? So the first concept, just to recap, was about hybrid system optimization. So here we're expressing the importance in, first, through computation, figuring out what the range of optimal design is. And that allows economic projections, including payback period optimization, but also looking at the CO2 emissions reduction. And so one of the things we've done, you can advance the slide a little bit more, please. One of the things we've done for clients who might, for example, in the government sector, who might have multiple buildings in a portfolio, is we will look at CO2 reduced per dollar spent over different buildings. So we can determine which buildings are the most rife for carbon reduction per dollar. Where should the money be spent first? And we do that in the context of hybrid system design, so that when we are installing a geothermal system, it's being effectively utilized. And the other point to reiterate, or I just want to recap, was about the ground thermal imbalance prediction. So here we're looking at cases where before installing the system, it's really important to understand how long the system will stay efficient for. And we want to project that out in advance when there's heating demand, for example, that's outpacing cooling demand. We will look at how that will affect efficiency. And I gave you the example of a solar assisted ground source heat pump planning and economic modeling. We've also looked at using dual purpose air source heat pumps that can provide heating or cooling, of course, gas boilers for peaking. And so the hybridization can often feed directly into the thermal imbalance, because an auxiliary system which can be used to optimize the economics can also be used to maintain system efficiency. Diagnostics and control optimization of existing and older systems is also very important. One, it lets us know if the system is still functioning as it was originally intended to, based on looking at what's happening with the ground temperature, what's happening with the energy flow, and also if a system is worth reinvesting in. So we'll look at systems that are sort of older generation, 25 years old, and we will say, yeah, this ground heat exchanger is actually quite healthy. Let's upgrade the heat pump, which is 20 years old. Or no, this ground heat exchanger is really unhealthy. If we're doing a retrofit, we need to have a larger solution. Is there any more on this slide? Yes, and CO2 emissions prediction. So all of this is underscored by the interest in making sure that we understand to what extent we're reducing carbon emissions. So I think that that's something that's pretty much always going to come into play. We always recommend, these types of calculations as an independent third-party recommendation. Most of the installers and drillers are honest, but it's always good to make sure there's a sort of an unconflicted view. If a building shouldn't have a geothermal system installed, like the ice rink example, it's important to know that in advance. And that's not something that an installer may tell you, of course, because it's contrary to their business. But I think having these types of calculations done in advance and alongside the installation is really important for that sort of understanding that the investment is going well and is being made aptly. So I think that's it. I see another question's gone into the chat. Jamie and I are happy to answer questions. I'll turn it over to Catherine to moderate or questions as needed.
Yes, looks like we're almost out of time here. A couple of minutes left. All the questions that have been asked and answered so far, we can document in the question and answer document that we will share. But I do have one more here. So heat pump technology in general. Oh, this is an answer, I guess, to the other alternative systems. So we had air source heat pumps, and again, yeah, heat pump technology in general, critical to meet climate change targets. Heat pump based solutions like closed loop ground source heat pump, open loop geothermal, wastewater energy transfer coupled to heat pumps, air source heat pumps. So there are other viable options here. Anything to add to that response?
Yeah, the one addition that I would have is it's just focusing on electrification. Electrification is necessary if we're going to move off of fossil fuels, we need to move into electrified options. It's going to be, in Ontario, we're fortunate that we have a very clean grid, but it's, that's the path. If we're going to reach net zero, it's going to be moving off of systems that have to burn, fossil fuels, and that requires electrification.
Right. Okay, this seems to everyone's questions here have been answered, but given we only have 1 minute left, I think if anyone has any additional questions for Seth or for Jamie or for us about geothermal, please email me. There's my email address here. Please email me your questions and I can pass those along to Seth, to Jamie, to other experts who can answer the questions. And we will make sure they get included in the question and answer document that will be posted on the website along with the recording. Okay, well, that was really, really interesting presentation. Really starting with the data is always that's how we operate. It gives you a really good foundation for decision making. So that was really, really helpful for me, and I hope it was for our other participants as well. So yes, thank you so much to Seth and to Jamie for sharing their insights with us today. And again, please feel free to email me any questions you have and we'll make sure they get answered for you. So thanks so much, everyone. Take care. Have a great rest of your day.